High, dry, extremely dark at night. Chile's Atacama Desert is one of the best places on Earth for astronomical observations. But there's a catch. The ground here has a tendency to shake, sometimes quite severely. This poses a major threat to Chile's people and its infrastructure, and it also has the potential to destroy the world's biggest telescopes, unless we develop some clever technology to protect them.
Having spent quite some time in Chile, I've experienced a fair bit of ground shaking. Modern telescopes are sophisticated, high-tech pieces of equipment, but they are also very delicate, and protecting them from the world's biggest earthquakes is a challenge unlike any other. The ground beneath your feet may feel solid and sturdy, but it's in fact dynamic and changing. The surface of our planet is covered by 15 tectonic plates, which move on average by about 1.5 centimeters a year. That's about as fast as your toenails grow. Chile, where ESO's telescopes are located, is situated on the boundary between the oceanic Nazca Plate and the continental South America Plate. Now, the Nazca Plate is somewhat denser than the South America Plate, so it tends to slip underneath it. Because the edges of the plates are jagged, they get stuck, and the pressure builds and builds and builds and builds and builds until, poof, shock waves are released, and we feel this as earthquakes. Here in Chile, tremors happen all the time. On average, we have about 2 tremors a day, but most of them are of no concern. However, every so often, a big earthquake will hit. Back in 1960, Chile was struck by a magnitude 9.5 earthquake, the strongest ever recorded anywhere. Such strong earthquakes are devastating, with a large loss of life and significant damage to the country's infrastructure, potentially including ESO's telescopes. ESO's Very Large Telescope, or VLT, is located here on Cerro Paranal, and it consists of 4 8-meter telescopes. Despite the region's strong tendency for earthquakes, it's still standing after 25 years of operation, and in fact producing cutting-edge science. So, did we just get lucky? Of course not. When building the VLT here, we knew we had to factor in earthquakes and find a way to protect the delicate 8-meter mirrors. But just how do we do that? Let's find out. Ironically, it's the technology that allows us to obtain crystal clear images of the cosmos that also poses the biggest threat to the mirrors in the case of an earthquake. In order to get perfect images, the mirror has to have the perfect shape. But due to gravity, it can become distorted depending on where it is pointing. This is particularly bad for big mirrors, like here, one of the VLT mirrors, that have a diameter of 8.2 meters and weigh 23 tons. In order to compensate for the distortions caused by gravity, we use a series of 150 motors, also called actuators, that adjust the shape of the mirror to make it spot on. The problem is, in the case of an earthquake, these motors can begin to shake and severely damage the mirror. Thankfully, the VLT has a trick up its sleeve. If a strong earthquake, say magnitude 7 or higher, hits, a complex mechanical system springs into action. At a moment's notice, the entire 23-ton mirror is lifted off the motors by a series of clamps around its edge and is secured to the telescope structure, thus keeping it safe. Over the past decades, Paranal has faced thousands of small seismic events and a few larger earthquakes, including in 2010 an 8.8 magnitude tremor that was the 6th most powerful earthquake ever recorded. Every time, Paranal's anti-seismic technology rose to the challenge magnificently, protecting the telescope. Okay, so we know how to protect the mirrors of the VLT from earthquakes, but these are only 8 meters in diameter. How about a mirror that is, say, 39 meters in diameter?
Just 23 kilometers from the VLT, ESO is currently building the ELT, the extremely large telescope. And it's not called that for nothing. This telescope will be simply colossal. To protect this beast, clamps and a sturdy structure just aren't going to cut it. Instead, the anti-seismic concept of the ELT relies on isolators that are placed below the telescope. Essentially, they separate the foundation from the ground. When there's an earthquake, the telescope, and in fact the entire dome foundation, can move horizontally on these isolators, if necessary by up to 30 centimeters, which is pretty incredible. However, when the Earth shakes, it does so not just horizontally, but also vertically. And in order to absorb that vertical motion, we have this part of the isolator here that works a little bit like the shock absorber on a car.
ESO's telescopes are like delicate giants, colossal and robust, and at the same time sensitive and finely calibrated. At the base of every great telescope is a great structure that is capable of adapting to the forces of the environment and compensating for the movement of the ground beneath our feet. This amazing feat of engineering means that the VLT and soon the ELT can work with as few interruptions as possible, meaning that us, the astronomers, can get back to the job we're here to do, unraveling the mysteries of the universe.